Hi everyone, my name is Marco Toschi from AI, and I'm here to share our project Relight My Nerf, a dataset for novel view synthesis and relighting of real-world objects. Traditionally, Nerf has been widely used for novel view synthesis, allowing us to generate realistic images from novel viewpoints. However, one limitation of the standard Nerf approach is the lack of relighting capabilities, which restricts its potential applications. We embarked on a quest to explore if there is a simple way to train a Nerf architecture that not only performs novel view synthesis, but also supports relighting of a scene. We then collected a specific dataset called Relighting Nerf, obtained through the coordinated movements of two robotic arms, one holding a point light and the other a camera. Moving forward in this presentation, we will analyze and discuss the results obtained with the proposed baseline. As mentioned earlier, the standard Nerf approach has limitations in terms of relighting performance, prompting us to explore related works that have made significant advancements. However, we realized that these approaches did not align perfectly with our specific research objectives. These methods proved difficult to train and required substantial computational resources. Our aim was to simplify the problem, providing a foundation for future research and enabling other skilled researchers to explore more sophisticated architectures. In light of the scarcity of real-world dataset with diverse object and ground truth light direction, we developed our own dataset. This unique dataset captures a wide range of objects and materials using real-world sensors, while incorporating ground truth light positions and challenging shadow casting scenarios. Now, let's focus on the problems we encountered and tackled during our research. There were two main challenges: acquiring an one layer at a time dataset and designing an architecture that could effectively support relighting. To address the first problem, we developed an innovative acquisition setup that involved the coordinated efforts of two specialized robots. Our setup consisted of a dedicated light-holding robot and a camera-carrying robot, working in tandem to capture the necessary data. These robots meticulously traversed waypoints uniformly distributed on hemispherical trajectories, ensuring comprehensive coverage of the scene. In this video, it is possible to witness the robots in action, capturing the images that form the foundation of our research. The camera robot captured high-quality images while the light robot maintained precise control over the lighting conditions. Through meticulous offline calibration and repeatable movements, we achieved a high level of consistency and accuracy in our data collection process. Within our dataset, we have curated a selection of samples that highlight the diverse range of viewpoints and lighting variations captured within the same scene. These samples offer a glimpse into the rich and comprehensive nature of our dataset, allowing us to examine the interplay between the viewpoint changes and lighting conditions. Now, let's discuss the dataset split we employed to test our architecture. The easy split involved rendering an image from a viewpoint never seen before, but under a light condition previously encountered. On the other hand, the hard split pushed the boundaries by rendering an image from a viewpoint never seen before and under a light condition that was also unseen. Moving on to the second problem mentioned earlier, let's explore the architecture designed to tackle relighting. This architecture, although simplistic, demonstrated promising results when applied to the carefully collected data we gathered. Now let's delve into the reasoning process behind the development of our architecture, as we iteratively refined it from instant NGP-like architecture to our final architecture V5. Each version represents a step forward in our approach, incorporating new insights and learnings along the way. In the first variant, we added a naive representation that encodes the position and orientation of the light source for each observation, using positional encoding with Fourier feature proposed in the original Nerf paper. This allows Nerf to start adapting to different lighting conditions. In the second variant, we changed the way we encode the position and orientation of the light, using spherical harmonics. Moreover, instead of using the same encoding for all points in one sample, we now consider the relative position between the light source and each query point. This seems to help Nerf to better understand the incoming light information. In the third variant, we introduced an additional embedding that represents the surface normal at each point in the scene. We also included the location of the point as input to preserve its spatial information during the network's computation. The fourth variant addresses the issue of different input scales in the previous versions. We modified the architecture to concatenate the surface normal embedding with the output of the first layer of the network. This ensures the compatibility between the inputs in terms of magnitude. Finally, in the fifth variant, we extended Nerf's capabilities by incorporating a physically based volume rendering technique. This technique allows for a more realistic representation of how light scatters within the scene, considering interactions between incoming light and surface properties. To offer a glimpse into the performance of our architecture, we present a selection of qualitative results demonstrating the relighting capabilities of the V1 and V5 architectures. These results offer a visual illustration of the evolutionary progression of our architecture over time, providing an understanding of its advancement and improvements. In order to assess their performance, we conducted a comprehensive evaluation using both easy and hard splits, as introduced earlier. In addition to evaluating relighting accuracy, we also examined the ability of our final network to capture and generate shadows. Shadows plays a crucial role in realistic rendering, as they contribute to the overall scene perception and depth. Finally, we present a video showcasing our experimental relighting network. The video features a comparison between ground truth images and our network's predictions. The top row displays the ground truth images, representing the true lighting conditions captured during data acquisition. In the bottom row, you will see our network's predictions for relighting the scene. By sharing our approach, we aim to inspire further exploration and innovation in the field of relightable models within the Nerf framework. Thank you for your attention. Scan the QR code to learn more about our project. We appreciate your interest and support. Bye!